This page is just a summary of the solution. And you can also label more energy levels here. Because what we have done here is we get this number. And we know the intrinsic Fermi level EI is in the middle, which gives you 0.55. That means this side is also 0.55. Then you can get the distance from here to here. This 0.55 minus this 4.19. Or in other words, by doping, by this p-type doping, you move the Fermi level from the intrinsic level, which is middle of the band gap, down to here. If you increase the doping to 10^17 for the p-type. Alright, so this is a practice again, and I will give you a few minutes. You can do this by yourself. And this is similar as the previous example. Ask where the EF in the energy band of silicon at room temperature 300 K, which will give you KT equals to 26 milli EV, which is 0.026 EV. And the first question is if the N-type doping, you have ND equals to this N equals to this 10^17. The second question is if NA equals to P equals to this 10^14. So maybe you can do the first one, the ND one. And I'll give you a few minutes and ask you what is the number there. Probably you need to use that NC equals 2.819 and NV is like 1.28, roughly let's say 2.9. So for those parameters, those constants, I will provide those numbers in your exam, and also maybe some key equations. So you do need some calculator. So that's why in the exam you need to bring your calculator, because you need to take that natural log, which you cannot do it without that calculator. So anyone get the number for the first one? So in the unit of EV,
EF minus EV is 0.984.
1.984. So the total band gap is 1.1 EV. and this Fermi level should be close to the EC.
0.146.
Want what?
0.115 if you LEC.
Okay, so let's look at the solution. No? Is this number? The same approach as the previous example. And then you plug in the numbers. Be careful. This is natural mode. It's not log 10. I don't know in your calculator it's log 10 or not. It's natural log E. So if you draw the Venn diagram, it will be something like this. And for the second question, P equals 10 to 14, then you will get this is 0.31 EV above the EV. So any questions here? I think you have this practice in your homework 1. So one more question. If we change the temperature condition, let's say from 300K to 400K, still for this silicon, so how do we do this? So the only thing you need to change is this KT. And at 300K, this KT is 0.026 electron volts. You just need to get KT at 400K. So you know KT is the thermal energy in the unit of the electron volts. Of course, this lowercase k is the Boltzmann constant, and the T is the temperature in the SI unit, which is Kelvin. Of course, you can use Boltzmann constant multiplied by the temperature in Kelvin, so you will get a energy number in the unit of joule, and then you convert back to the electron volts. But you don't need to do that here. So a simple way to do this is just look at the ratio, right? Because everything is proportional. This KT, if you increase temperature from 300K to 400K, that means this KT will also increase in proportional to this change. So what you can do is look at the ratio. Because you know at 300K is 0.026 EV. So you get the 400K, that is 1.3 times that number. And then you can plug in this KT to here. Any questions? So, one more question. Okay. If we further increase the temperature, where would be the Fermi level? So the Fermi level, where would be the Fermi level if we further increase temperature to 500K? Any idea? So from this 400K case, you see that EC minus EF, that number will increase, right? This is in proportional to that change. So that means it will be lower. So let's say this is 300K, the EF is here. 400K, probably EF is somewhere here. Right.
Should more electrons go into the conduction band?
No. From that equation, you get a larger distance between EC and EF, right? That means lower. I mean larger distance, right? And then to the extreme case, if you increase the temperature to maybe, let's say, 1000 K, then you will find out your EF will be further down, and then it will be in the middle of the band gap, almost the intrinsic level, EI level. So why is that? Any idea?
Because you free more electrons and the doping effect is eliminated.
Exactly. So as you increase the temperature, okay, so you are going to get more thermally activated electron hole. We talked about earlier, right? So there are two ways to introduce the electron hole. One is by this intrinsic thermal vibration. You break the bond, then you get the electron hole pair. But at the room temperature, the probability is very low. So the electron is dominated by the externally dopant, right? You have the dopant. So that's why you have the Fermi level close to the EC. But when you increase the temperature to the very high temperature, like 1000 Kelvin, then you are going to have very large thermal energy. Then you basically breaking many bonds. So you create a lot of intrinsic carrier, electron hole. And then the external doping is less important because everything, all the carrier in the system is by the internal thermal energy. So that means the external doping not important. Everything becomes intrinsic. If it becomes intrinsic, then of course Fermi level goes to the middle. Of course, at a very high temperature, then all the bonds break, and then the crystal no longer exists. Then the melts basically, right? So
if you're below the Fermi level, you go up.
Yeah, if it's P-type
You're
doping,
below the middle point.
yeah, you merge to the middle. Yeah. All right. So just more discussions here. So the last point in this lecture is the comparison with metal in terms of the resistivity. So if you recall the lecture 2 on the metal interconnect, we talk about the aluminum and the copper, and then we have this table, the mobility for the copper or aluminum and the electron density. So those are the electron density for the copper, and then we get the resistivity. So how did we get this resistivity, if you recall there? So we get the sigma, which is conductivity. You can check the lecture slides there. You get Q n mu, and the resistivity is 1 over sigma. So you get resistivity 1 over Q n mu. Q is, is a basic charge quantity. That is the charge one electron carry. N is the electron density. Mu is the mobility for the electron. So you get this number. This is for electron. So if you have hole, similarly you can think it's 1 over Q P mu. Then we look at the silicon here. So here is the mobility for the silicon. For example, for the electron, here we have this 1400. And then if the doping density is this 5 times 10 to 18, then you can plug in the numbers to get the resistivity. And then the other doping level, this is for N-type doping, so that means here you have NB. Here you have NA for the P-type. Then you can plug in the numbers and get the resistivity. Something like this. But here this number actually is not correct. As we discussed in the next lecture 6, we'll see that mobility here is not correct here. Because right now what I showed here, this mobility is mobility for the undoped intrinsic silicon with the doping. this mobility will change. But let's say to the first order, we assume this is the same. Then you can use this number and multiply mu n and q. Then 1 over that, you will get the resistivity here. And this range 10 to the power 15 to 5 times 10 to the power 18 is a typical range for the doping we discussed earlier. So that is a typical range for doping. And to the higher end, you can have 5 times 10 to the power 18. To the lower end, you have 10 to the power 15. So with different doping level, you can see that the resistivity can be tuned of the silicon. So you can make silicon more conductive or less conductive based on your doping. But still, if you compare the silicon with the metal, even for the highly doped case, then the silicon is still more resistive than the metal. So in the integrated circuits, we typically use silicon, heavily doped silicon, for some local short distance interconnect. You can make interconnect wires with doped silicon, but only for short distance. For example, if you connect one transistor to the adjacent transistor, then you can use the doped silicon, heavily doped silicon as the metal wire, like metal wire, not really metal, but the resistivity is kind of low if you heavily dope. But if you talk about the global interconnect, non-distance interconnect, then you have to go to the real metal, like copper, for that. Any questions? All right, so this is for this lecture 5.